We're going to continue with part 2 of the lecture of David.
Okay, thank you. So I have to remember what I was going to say. This is the nonlinear Ekman effects. So here I won't be worrying about, I'll just assume that we know tau, right? So maybe it depends on the ocean velocity, maybe it doesn't. I'm just assuming that we know what it is. But instead of taking the Ekman transport to just be balanced by the wind stress, the Coriolis and wind stress, I'm going to allow for nonlinear or sort of advective terms to come in. So there's u Ekman dot grad u geostrophic and u geostrophic dot grad u Ekman. So at this point, I'm still assuming everything's slowly varying, so I don't have a du dt term here. But I'm allowing for the surface currents, which again are taken to vary slowly in the vertical, so that any z derivatives are only in the the ug is constant with z over the Ekman layer. And so early work dates to Melvin Stern, and essentially says that the Ekman pumping, instead of being the divergence of a vector perpendicular to tau divided by f, it's well divided by f plus zeta. And that comes from two things. One is sort of a scale analysis here, where you can look at this term and argue that this first term, u geostrophic dot grad Ekman, is small compared to u Ekman dot grad u geostrophic. And the idea is that even though when I take the curl of it, my wind stress might show all these sort of ocean current structures, the stress itself, and so the Ekman transport itself, is still dominated by my u base, my tau base, which is dominated by large-scale winds. So grad u Ekman scales like, 1 over the length scale of the winds, whereas grad u geostrophic scales like the current. So if I take the ratio of, let me get it right, of this one to that one, I get something that goes like a kind of an ocean scale divided by an atmospheric scale, which is, the ocean width of the Gulf Stream is maybe 100 kilometers, and we think of 1,000 kilometers as the width for the atmosphere. So the idea is to leading order, drop this term and just worry about that one. And if you imagine just an eastward stress over an eastward current, so my current, both tau and u don't only depend on y, so to speak. And I just look at, what's u Ekman dot grad u geostrophic? Well, my u geostrophic is just u, and it only varies with y, so I just get a v Ekman d by dy of u geostrophic, and that's balanced by tau f. And so when I solve for, v Ekman, I just get that it's goes like tau over f plus zeta, if you will, f plus the relative vorticity associated with this plane parallel flow, this sort of straight current. And u dot Ekman will then be this formula given by Stern. But you can imagine the same eastward current, but a northward stress blowing over it, right? So u depends only on y, but my Ekman velocity is going to be, I have the stress is in the y direction, so the Ekman transport's in the x direction, so I get a u Ekman d by dx of u, but that depends on y, and then there's no v Ekman, so this stuff is 0, and I just get the regular old formula back, right? So you could modify Stern's formula by just saying, kind of like I did with my u tilde before, I have, it's del cross, the formula is given by, the transport, the Ekman transport, the thing that I'm taking the divergence of, is splits into two parts. In other words, if tau is parallel to the current, you divide by f plus zeta, and if tau is perpendicular to the current, you divide by f, and it gives you a sort of modification to that. A little bit more recently, Winograd and Thomas, 2017, put this term back in. So they said, well, you know, sometimes it's important, let's look at it. And they went away from worrying about just sort of plain parallel flow to worrying about currents that, you know, meander and go. So they were really concerned about the curvature of the flow. And they did everything in streamwise coordinates, or sort of natural coordinates, where S, I guess, is parallel to a streamline and N is perpendicular to the streamline. Yep. Sure. You want the W's or what?
Use them.
Well, it's the momentum equation.
Yeah, of course, but you have, if you split up into UG and Ekman and take the nonlinear terms, I guess.
Oh, so there's UG dot grad UG, for example. Okay, so fine. So UG dot grad UG is but that's already taken care of by the geostrophic flow, okay? And that extends through the Ekman layer, and that's helping me determine what the geostrophic flow is doing in response to the Ekman problem. I'd also have U Ekman dot grad U Ekman, and I'll talk about that a little bit. And that's typically small, and also it's hard to do anything with formally because U Ekman depends on Z, okay? And if a quadratic term, I can't just integrate through it conveniently, right? So one answer is that it's hard. And I mentioned at the end, I'll talk about these leads in the Arctic where the stress varies on a very small time spatial scale, like 10 meters or so across a lead. And there, the Rossby number based on the Ekman flow, so sort of U Ekman divided by FL lead, is huge, right? So it's not small at all. And there, you do have Ekman-Ekman interactions. And so that's the very last couple slides of my talk, right? Okay. Anyway, so they come up with this system of sort of coupled characteristic equations. You know, you have to do an integral, a line integral along the streamline. And I don't want to get into the details of their equations. Omega is sort of the curvature part of the vorticity, and epsilon is the Rossby number, and so forth. So you can do this integration and get UG, and they did it for some simple flows. So this is an eastward flow over an anticyclonic eddy. So going like this in the northern hemisphere, and this is their W. And this is the difference between their W and Stern's formula. And it wasn't clear if they used what I call the modified Stern's formula or Stern's formula, but you see that, you know, there are order one differences here. So anyway, you get a different solution. And so it's a nice study, but I wanted to look at it in a kind of turbulent setting, right, where you at least have something like QG turbulence that we're applying this to. And imagine doing a line integral on a turbulent contour that's all twisted and snarly might be a bit of a problem. So I wanted to get away from this kind of integrating along characteristics. And so that's work that we did with Louis-Philippe and Yanshu Chen. She was a master's student. She's now a postdoc at Woods Hole. And so the way we thought about this was we wanted a sort of a simple model. We called it a toy model at the time, but the reviewers didn't let us call it a toy model for some reason, so we called it a simple model. So it's just a two-layer, doubly periodic F-plane shallow water system. So I have, layer one, layer two. There's a density in the top layer and a density in the bottom layer, so oil and vinegar. And there's a rigid lid, and it just obeys the shallow water equations. But in the upper layer, I embedded a slab, okay? A slab layer. So normally what you would do in a two-layer or multi-layer shallow water model, if you wanted to force with the wind stress, you would apply the wind stress as a body force distributed over the upper layer, right? Because it's a shallow water layer and you don't have any vertical resolution within the layer. So you just say, well, it's a body force distributed over the layer. So that would be the usual way of doing it. What we did is we applied the stress to a kind of an Ekman-like nonlinear Ekman-like equation, but this time with the du dt term, okay? And then that's going to give us a slab layer transport, so a horizontal transport in the slab layer. And I can take the divergence of that transport, and that shows up in the mass continuity equation for the top layer of my two-layer shallow water system, okay? And I have two versions of the slab layer, and this is a cheap attempt, misrepresented attempt to get one of the terms that Carson was asking me to put in, sort of u slab dot grad u slab. So I can't really do this because, I can only talk about u slab. The capital U means it's a vertical integral, right? A transport, meters squared per second. But I'm integrating through something that has some vertical structure, and here I'm making the sin of saying that the integral of a quadratic is the quadratic of the integral, right? So it's not strictly true, right? But I'm going to do it anyway. So this allows for sort of a Ekman-Ekman interactions, but it's also going to notice that I'm going to get inertial oscillations here, right? So this set of slab layer equations are going to give me the nonlinear Ekman stuff, and they're going to give me inertial oscillations. And the D here is a dissipation, right? So I'm going to add horizontal dissipation to this problem just because you need to for numerical instability. But my slab layer transport is going to wind up with slowly evolving components, which are basically the Ekman or the nonlinear Ekman part, and fast evolving components, which are basically modified inertial oscillations, right, or near inertial oscillations, if you will. So I'll have these two versions of the slab layer, and the difference between them is just whether I have this Ekman-Ekman interaction or the kind of near inertial Ekman interaction. Okay, so we redid this problem from Winograd and Thomas and got something similar. It doesn't look exactly like theirs, but it's an eastward stress over an eddy. They didn't tell us the structure of their eddy, so ours is different. I think this side's anticyclone and this side's cyclone, and this uses the version of our slab model without the self-interaction term. When I say the self-interaction term, I mean the slab interacting with itself, and this includes it. And so I have just a uniform eastward stress blowing over the eddy. So the stress is just to the east, and that's it. There's no ocean velocity dependence or anything. And this is my Ekman pumping that I'm getting out of that. And in this case, the uniform stress also includes just a southward transport. And you can see the southward transport is kind of blowing the nonlinear Ekman structures off of the eddy, right, to some extent. So anyway, a little bit of stuff going on there. So the self-interaction term includes a sort of southward or transport of the perturbations in the slab layer velocity, so the nonlinear Ekman stuff. So we did so it's a doubly periodic domain, just an F plane, with a nice wind stress. So again, the wind stress itself is just a cosine or sine, depending on where 0 is. So it's eastward in the middle and westward on the ends, and it's periodic. And you see that you get this wave number 1 structure with upwelling here and downwelling here. So, this is cyclonic forcing and anticyclonic forcing. But you also get, this is after the models equilibrated, you also get this structure, that's starting to look a little bit turbulent, at least in the Ekman pumping field itself, right? So this would, if you care about biology and stuff, this is moving nutrients up and down, and somebody else was talking about moving carbon up and down yesterday, I think, and so this W is going to do that. This is just to give you a vague idea of the surface layer speed, just to give you an idea of the, so it's it's not QG, it's shallow water turbulence, but the turbulence is kind of like QG turbulence, and it's on an F plane. I have a strong damping to kill the inverse cascade, and this is, just to get some hint of the sorts of nonlinear Ekman pumping that you get out of it. This is a Hofmüller plot. So time on the x-axis and latitude or y on the y-axis of a spin up from rest of that previous simulation. And the field that I'm plotting is just W, right? So when we started it from rest, we're going to get this this sort of wave number one, blue in the blue in the lower half of the domain and red in the upper half. But superimposed on that are, of course, inertial oscillations. If I just switch on the stress at time t equals 0, I'm going to get these inertial oscillations. So that's what these little stripes are. But you see that, something's happening, and what's happening is different in the anticyclonic side than in the cyclonic side. And this is a continuation, or well, this is going from 1 to 150 days or so, and this is going from 0 to 2,000 days. And so this, structure, you keep seeing this strong asymmetry between what's happening in the cyclonic and anticyclonic side. But eventually, around here, baroclinic instability sets in. We start getting eddies, and the eddies get richer and richer. And the eddy field eventually stirs up these inertial oscillations, and they go away, right? Because the geostrophic eddies are just stirring up the inertial oscillations, and I have a small scale dissipation that just kills them, right? So I wind up, after, 2,000 days, I wind up with a field that doesn't have these high frequencies in it, right? So it's just my nonlinear Ekman pumping. So these little stripes are time slices, and these are X, Y plots at these three different time slices. I kind of like it because this one, so it's here, looks a lot to me like that, right? Except that the last little bit of this plot, the x-axis is still time, whereas here the x-axis is x. So I guess it's a sort of an illustration of ergodicity or something. But so anyway, so that's that problem. So what's that? And this is, I didn't say, this is for a simulation where I kept this self-interaction term. If I didn't keep this, there would be a symmetry between the two sides, and I wouldn't get this sort of structure. Okay, so let's make sure I said everything. The high frequencies are very different on the two sides, and then the geostrophic flow eventually gets rid of it once it kicks in, once it goes unstable. Okay, this is for a similar simulation, but in addition to my steady forcing, right? This one was forced with just steady winds that looked like this. I took this same wind structure and just kind of jiggled it around, right? So I added to it something that just follows an Ornstein-Uhlenbeck process, but it just puts energy in at higher frequencies. And this is what I get. And so, here's my frequency spectrum plot. The Ornstein-Uhlenbeck, there's a huge range of scales here. So my Ornstein-Uhlenbeck peaks at 5 days, right? And then sort of falls off. So it was meant to be like synoptic scale forcing in the atmosphere, but even synoptic scale forcing is going to have some signature at F, and that forces a huge response in my inertial oscillations, which remember are misrepresented in that the inertial oscillations, there's no dispersion of the near inertial waves. The two simulations are for the linear version of my nonlinear Ekman equations. In other words, for the one without the self-interaction term and the one with the self-interaction term. And again, you can see this is the anticyclonic part of the forcing. And you see a lot more high frequency activity. So I don't have one, but if I had a movie of this, you would see these little stripes switching red to blue, red to blue, red to blue on the inertial time scale, and then sort of slowly evolving on the advective time scale. So we wound up with this, this high frequency component of the slab layer divergence, but mainly in, or preferentially in, well, here you see it sort of at these latitudes where the winds are maximal, maximum to the west here and maximum to the east here and back to the west. So this is plotting a kind of an RMS. The red curve is an RMS of this activity. And the blue is an RMS of this activity. So there's much more of the zeros over, zeros off the, to the left of here. So I get more activity in the anti-cyclonic side. So there's this difference of behavior. And then I want to, so here I have near inertial, you can't even see the sort of wave number 1 structure of the flow because these are just much stronger, okay? Okay, so this added near inertial slab layer W is, you know, you might think it's just due to what I had said before, the large scale Ekman pumping kind of pushing the stuff from one region to the other, like into the anticyclonic area. Remember I'd said a few slides ago that one thing this nonlinearity can do is that the Ekman, the large scale Ekman pumping can sort of push the activity, well, in this case to the south, but more generally into the region where it's converging, so into this. So, you know, we thought, well, maybe that's what's happening, but it's not. It's due to an instability similar to an instability described by Weller a long time ago. And so Weller was interested in an instability between inertial oscillations or near inertial oscillations and the divergent part of the geostrophic flow. So we're used to thinking of geostrophy as non-divergent, but there's an order epsilon divergence. And he showed that that order epsilon divergence can interact with near inertial waves, and there's a sort of instability there. For geostrophy, you know, it extends throughout the water column, but the divergence is small. For the Ekman layer, well, it's just the top of the layer, but the divergence is big, right? But we see the same instability, but in the Ekman layer. Just to sort of simplify it, I want to think of my slab layer as sort of an Ekman part and a fast part that are denoted with a prime for some reason. And so my U slab.grad U slab is going to be a U Ekman dot grad U fast and a U fast dot grad U Ekman. And if I'll simplify a little bit and just say, well, U Ekman is dominated by just the large scale sinusoid, so just the V Ekman times Y hat, and my W Ekman is just the Y derivative of that, then what do I get? When I get, I'm going to get a partial derivatives of the fast U Ekman and V Ekman, or slab and the Coriolis terms. I'm going to get an advection by the Ekman velocity, so this, so V Ekman d by dy of each of these. And then I'm going to get a V Ekman d by dy of U Ekman, which is shown over here, right? So this is just I'm just sort of simplifying this, my equations a little bit to explain this instability. And I'll simplify it even further by just considering this latitude here, where the W is maximal, right? Maximum downwelling, and the wind stress is 0. So V Ekman will go to 0 there. And so my equations simplify. And I'll just, this is sort of almost trivial. I mean, you just take another time derivative of this. So I get a time derivative here, but that goes like, you know, F squared V. And I get this equation for V prime. So 2 time derivatives, 1 time derivative, and F squared. and my sigma is sort of related to the Ekman pumping velocity. And you all recognize this as a damped harmonic oscillator, but it's damped if sigma is positive, and it's undamped or negatively damped if sigma is negative. So if W is negative, so downwelling, so an anticyclonic stress, I'll get a slow growth of my primes, and that's what I get, right? So, slow growth of the primes, and so my Ekman, my fast time scale slab layer transport, sort of, it grows here and it decays there through this mechanism. And again, there are other mechanisms that say, propagation should make it leave here and go to here as well, but that's something else. So in this case, the damping is in the anticyclonic part of the flow, but it's really the anticyclonic part of the forcing. So going back to the first part of my talk, if we had a flow-dependent tau, the cyclonic forcing is going to be over anticyclonic eddies, right? So we think of the near inertial energy as rapidly leaving cyclones and accumulating in anticyclones, but in anticyclones there's a cyclonic forcing, and I'll get a slow damping of near inertial oscillations in the top part of these anticyclones out of this mechanism. Okay. Okay, so this is the work with Jan and Louis-Philippe. I was playing around with this, I called it a toy model, it's sort of two-layer, yeah.
See, the instability that you showed, previously we had talks which described the inertial oscillation, the spatial scales decreasing and they going down through these anticyclonic vortices.
Yeah, okay.
Which phase would this be relevant? Would
this
it be before
would be
that?
right at the top, right? So the anticyclones are, sorry, the near inertial forcing would normally be large-scale winds, right? And that's going to get imprinted on the eddy fields. It's going to propagate horizontally out of the cyclones into the anticyclones. That's not in my model, right? But that would be in Pascal's simulations, for example, and accumulate in the anticyclone. And it's going to go down in the anticyclone, like she was suggesting. That also is not in my model. But to the extent that some of the near inertial oscillations stay at the top, they're going to get damped by this mechanism.
Okay, so this will go parallel to that. This will go parallel to that.
Parallel to that.
Parallel in time, sort of, at the same time.
Yeah, it would be happening at the same, well, it's just not in this model, right? This is a, yeah. But. Okay, so we wanted to, move away from, a two-layer model with kind of unimpressive geostrophic turbulence to get a little bit more towards realistic models, and we're not quite there yet. So these are kind of 2.5 kilometer resolution simulations with 100 and some odd points in the vertical. So decent resolution, it's like a meter resolution at the top, and it kind of goes down, decreases going down. And it's the arrows are showing the wind stress. This one does have an ocean velocity dependence, but the wind stress is basically a structure like that. It's big in the middle, to the eastward everywhere, but it kind of goes to zero at the edges. So kind of like a cosine squared structure. We have a ridge here because it's an eastward wind stress in a channel. There's a, it's a kind of a long, skinny channel, so about 2,000 kilometers here and 1,000 repeating channel. And when you have an eastward wind stress over a repeating channel, you need topography, otherwise you'll get huge currents, right? So we put a ridge in for that. So this just gives you an idea of the regime. This is surface temperature, a snapshot, and surface vorticity, well, not surface, but below, 11 meters. You could quibble about whether that's a in or slightly below the mixed layer, but this is our vorticity. And it's not huge, right? But just to give you an idea of what kind of regime we're in. So depending on where you are in the domain, there's 5 to 8 or so grid points per Rossby radius. So it's eddy resolving, certainly, in places sub-mesoscale permitting, maybe. And we tried to turn off as many of the bells and whistles. It's a MIT GCM simulation, but we just use a constant eddy viscosity. I think there is a scheme to adjust if the flow is statically unstable, but we turned off as much of that as possible. And and here's my nonlinear Ekman equations, but I don't have this self-interaction term. And I'm going to take U geostrophic. Strictly speaking, it won't be geostrophic anymore. I'm just going to get it from the model. So I'll just take U below the Ekman layer, and we try, it doesn't really make that much difference if I use 20 meters or 10 meters or 30 meters or something else. I get essentially the same, the same field. And so my U is varying slowly in Z, but it's just a model velocity. And I plug it into this equation. Tau, I know what tau is, and I used viscosity. The actual model, I think, used biharmonic, but in our Ekman equations, we had to use harmonic. But it's called the nonlinear Ekman dynamics, but this is a linear equation. In other words, I'm taking U geostrophic or U model to be known. So this is just a linear equation with variable coefficients. The variable coefficients are the U's and V's. And so I can solve it with just, it's just AX equals B, right? It's just a big matrix problem. And we used a GMRes method to solve it for W. And here's our Ekman GMRes solution for W. And here's W kind of at the base of the mixed layer from the model. And, I was expecting them to be, to see hints of this one in this one, but I wasn't expecting it to be quite as good as it is, right? So I was sort of surprised. So there's big differences near the edges, right? Near the edges, my stress is very weak. So any of this is not Ekman because the stress is basically zero. But you see certainly a lot of correspondence. It looks like the colors are a bit more saturated than in this one. In the next slide, I'm going to kind of blow up around this little feature and maybe change the color scale a little bit. So this is my Ekman one. This is the model. And this is just a coarse-grained version, a smooth version of this one. So just a 9-point smoothing that kind of halves the resolution, if you will, using neighboring points. And now these two really do look very similar, right? So at least I was impressed that this simple theory works as well as it does. Okay, and we played around with trying to make it better, like you might add the du dt term by just doing this, getting this field at successive time steps. These are, I should have mentioned, this is a one-day average of the velocity field, and my Ekman is based on one-day averages of U and so forth. But we can do it for 3 successive days and try to put the du dt term in and try to kind of play around with it a little bit and make the correspondence, a little bit better, but that didn't really lead anywhere. This is this simulation had a version of the ocean surface velocity dependence in it. So I just used the one that was already sort of standard in the model. And so this is a plot of the, the curl. So if you multiply by roughly -10 to get a W Ekman, because there's a divided by F and it's southern hemisphere. And anyway, there's a rho naught and a F that gives you about a factor of 10. But so 10 to the minus, this will become 10 to the -6. So the W Ekman associated with this eddy killing stuff is about 1/10 of what we're seeing here, right? Okay, so this is bigger. The one here uses the same U and V, but when I went to solve my Ekman equations, instead of using the ocean velocity dependence in tau, I took it out, right? I just used tau to assume that it didn't depend on the ocean velocity, but the currents were the same. The currents came from the simulation with the ocean velocity dependence. So this is my offline, GMRes calculation of W with and without the surface velocity dependence included. And, these structures are basically the same. I kind of thought that all this rich structure in the forcing, in some sense, in del cross tau, would lead to a richer structure in the nonlinear Ekman. And you do see differences, right? If you look at this eddy here, it's blue, so blue means negative, but if you multiply by -10, it would be red, which would be positive. And you see this is sort of filled in compared to its sibling over here. So you certainly do see effects. And in fact, the nonlinear Ekman the linear ocean velocity Ekman pumping stuff is kind of in this nonlinear solution. But the sort of, I'll call it submesoscale structure is not really related to the ocean velocity dependence. You see it even if you don't put it in this Ekman calculation. Okay, so we wanted to do several things. One is higher resolution and sort of forcing getting a mixed layer that's more like winter conditions to get a more robust submesoscale, and we haven't had time to do that yet. But we also just wanted to force with high frequency winds in addition to the low frequency. So here's just taking my wind stress and adding plus or minus 20% to it, and this is plus or minus 50%, and these are daily mean W's, the model W. The one I had before, the control simulation, it's a different time snapshot. This is these are low pass filtered versions of a W that also includes a high frequency wind. And you see it starts to look a little bit different. Clearly when I go to strong near inertial forcing, if you will, I'm going to get W's that look very different from my Ekman calculation. So these would have essentially the same. If I did my Ekman calculation, these would look basically the same, right? Because my tau averaged over a day is going to look basically the same even with the high and low frequencies. But there's a low pass W that results from the wave forcing or the high frequency forcing. So this one is this one, I think. And this is the daily average, and this is the snapshot. So just to give you an idea, there's a lot more going on in the snapshot. Let's see. This is comparing my GMRes and my modified Stern, and modified Stern, and they look. It's not that bad, right? GMRes is just really an expensive way to do this, in a sense, right? There's some differences, but the main difference is that my W is now, less similar to my nonlinear Ekman calculation. So my low pass W is less similar to my Ekman calculation than was the case when I did not have the high frequency forcing. And so I'll recap and just say where I want to go with this, but unfortunately I haven't gotten there. So I'll just sort of outline a couple of next steps. So this, I think I said, well, without high frequency forcing, the nonlinear Ekman theory does pretty good, right? And I'd like to do that in a simulation with a more robust submesoscale. Mine's kind of doesn't really have that, and I just haven't gotten there yet. But even in the simulations that we have done, you could call it, if you want to be generous, you could call it submesoscale permitting. When we add the high frequency forcing, the low pass W diverges from this theory. And I have a kind of way to think about this that I'm hoping leads to something. So I'm claiming this might be related to nonlinear interactions between the waves and this high frequency component of the slab, not the slab flow, but the Ekman, the frictional flow. So in other words, I'm claiming that I want to take the model, the non-Ekman model velocity, so sort of, before I called it UG, but U just sort of from 20 meters or so below the Ekman layer, and split that into a slow part and a fast part. And similarly for my U Ekman, my frictional part, I'll split that into a slow part and a fast part. And so I mean, this decomposition is just, well, I'll just output, hourly snapshots and average them together to get a slow one and take the difference to get the fast one or something like that, right? And this one, well, if I want the slow, I just use my GMRes and I solve it. And, I have the slow tau, I have the U slow that's accessible, and I can solve that and I get U slow. My slab model, or I'll use a slab model to get the fast component. And so that's going to have, a time-dependent term, a U fast. So think of this as like near inertial waves, maybe. U near inertial dot grad U slow, the slab, this, and then U slow dot grad the waves, and then I have a Coriolis term and the fast part of the stress, and so I can get this, and you might say, well, okay, I integrate this equation. It's going to depend on initial conditions, but I want to claim that there's a particular solution and a homogeneous solution, and I'm hoping that the homogeneous solution sort of decays, right? Gets sort of stirred up and decays, and that you're left with a sensible, a unique solution for U fast. So then I can take U fast Ekman, U fast wave near inertial from below the mixed layer, extending through the Ekman layer and below, dot grad just the part in the Ekman layer and vice versa, and I can take a low pass filtered version of that and just add it to my to this, and then redo this, right? Redo this, but with F, and so now I have a different U slow, and maybe I have to do that again, and but I'm hoping that will lead to something. So well, I'm running low on time, but so this is just, here's my slow vorticity, and this is supposed to be a dot here, but here's my slow divergence and the fast divergence. And anyway, we're looking at that, and this was supposed to be a movie, but it doesn't work. But if I ran it, you would see, it's showing the slow and the fast, it's a transect, and you see that the fast, slow, that that you have the waves that look like they're not really varying with Z below the mixed layer, or over this domain, but there's a clear difference in character in this upper 20 meters or so, and that kind of, sometimes it's 10 meters, sometimes it's 20, it comes down to 30, it kind of bounces around a bit, but the point that I'm making is that there is a frictionally modified part to the near inertial oscillations that might be worth thinking about, right? And might be help to explain near surface vertical velocities. And well, this is just my extra slide about the Arctic. So there's pictures of sea ice, and it's not really the best picture, but if you imagine an ice-covered ocean and the ice is moving, and the stress on the ocean is just the ice ocean stress. And if you imagine a lead, like one ice flow moving past another one, so the stress on one side is this way, and the stress on the other side is that way. And, this might be 10 meters across or something, sometimes it's close enough you can just sort of hop over it, right? And so the stress might be weak, right? But the derivative of the horizontal derivative of the stress is huge, right? Because the scale is small. So my Ekman nonlinearity is going to be important here. And so I talked a bit about nonlinear Ekman theory, and I claim that's a misnomer because I solve for it using a linear solver, right? I mean, if the geostrophic currents are known, well, it's just linear, it's really a linear equation. But if I have to account for the Ekman nonlinearity, then it truly is nonlinear, and that I claim happens in this situation. And there's a strong asymmetry depending on whether the forcing is cyclonic or anticyclonic. And the figure's not that great, but this was another student, Pascal Bourgault, and with Louis Philippe as well, and Bruno Tremblay and Kevin Duquet. But it's just, we did an MIT GCM simulation, and it's just a constant density fluid with a specified stress. And we have delta X is delta Z. It only goes down 50 meters, and I forget exactly how, it's just as wide as we could make it with the computer time that we had. And so it's periodic, so the stress has to be periodic. But we have a sharp, this is meant to be the lead, so it's going one way here and the other way there. And then I have to, the lead would really just be constant on one side, jump, and constant on the other side. But we were constrained to make it periodic, so we did it like that. And one way is cyclonic and the other way is anticyclonic. We also had the middle one is for when there's a, what do you call it, a buoyancy flux where the lead opened up. But this is for the case, this is like this is just a blow up of the upwelling case. So a blow up just sort of in this region here where the sharp gradients are. And you don't see anything in the upwelling case, and you see a lot of strong downwelling current and a lot of turbulence in the downwelling case. And I think I've overstayed my welcome, but you can understand that just from a simple 2D model in this plane that kind of, if you think of y as along the axis of the lead, so in the XZ plane, you get, vorticity equation, but a coupling term is a, F dv dz, and that's one sign on one side of the lead and the other sign on the other side of the lead. So as a parcel's kind of coming in on either side, it's getting, plus VZ here and minus VZ here. You get a discontinuity, and you get a vortex dipole that dives down and makes a sharp current. And this is 2D, but if it's 3D, it goes unstable and gives you a sort of a mess like that. So anyway, that was just another Ekman-related fun problem that we did. So that's it. Thanks.
Have time for questions and discussion.
No, it works. The last slide here, can you argue that this is somehow
important? You still have to
important?
hold it closer to your mouth, I think.
Can you argue that this is somehow important for?
No, I can't, but I just argued that it was fun. We were claiming, so people have looked at this. There was some kind of famous campaign in the Arctic where they set up their tents, on the ice, and a lead sort of broke the camp and they had to kind of run and move. It sort of broke it up. And then someone had argued that the sense of the lead was upwelling, and they were arguing that the upwelling brought a very strong heat flux, that might melt the ice. So we were thinking, if there are all these leads going around and some of the leads are upwelling, some of them are downwelling, it might transport heat from, deeper down, bringing, the Arctic is salinity stratified, right? So the surface waters are at the freezing point and they're a little bit warmer below. There's just different water masses and such. There was a suggestion that it might be strong enough to bring, sort of vertical transport of heat into the surface layer where it can interact with the ice and melt the ice. And that was sort of the motivation of this study, but we didn't, I wouldn't say that we concluded that that was important.
Like, can we use this sort of theory to understand the heat transport across ACC?
So which part?
Like this one, when you were talking about if two sort of currents are coming in, so they go down.
Oh, okay,
as a
so
sort
no,
of
I would say no, right? This is like a very small scale, nonlinear stuff, right? So the heat transport across the ACC is, I mean, I suppose there's an Ekman component, but it's mainly the geostrophic turbulence. I think that's responsible for most of that. And
but there are outcroppings of the isopignals in the ACC regions and pinching of the eddies as well from the ACC.
So there's outcroppings of the isopignals in the ACC. There are none in this model. It's just water it's just fresh water, right? But yeah, I mean, I guess I'll answer sort of more generally. We care about, why do we care about Ekman, right? Pumping, well, okay, CO2 sequestering maybe, or biology, or whatever tracers you're interested in, are going to be, well, advected by, the Ekman current, well, by W in general, okay? And I think people that look at that, look at fine scale, submesoscale structure in W, aren't really thinking about the Ekman equations. There's sort of a lot of the work has been done for very sort of smooth currents, a constant wind over a kind of boring current, and a lot of the people looking at sort of submesoscale circulations around fronts, there's a W even if you turn off tau, right? And so, but I'm saying, there is a surprisingly rich structure to the Ekman pumping part of this equation. Not to say that there's not also the non-Ekman part, right? And I was just trying to see how far you could push this theory, right? So,
Any other questions?
The calculations that you presented, inertial oscillations, these fast fluctuations, there's a transient phase where they were being damped, right? But this wind forcing with high frequency waves, they're persistent in the upper ocean.
Sure, right. So I did one problem that was an initial value problem, okay? And this was this slab model thing. And so I switched on the wind stress at t equals 0, so there's a shock, and so there's inertial oscillations generated by that. And those persisted for a long time because there was nothing, the whole flow was boring until it spun up and went baroclinically unstable. But once that happened, the geostrophic eddy sort of stirred it up and got rid of them, right? On the other hand, if you continually put them in, right, through variable winds, well, then they're always there, right?
Would that lead to a permanent effect in the result? Would they be a...
Yeah, sure. Well, permanent, what do you mean? A low frequency part of the W, yeah.
And a high frequency component too, the nonlinear
yeah, high frequency too, right? But I was, yeah, so there's going to be, so I'm claiming that the high frequency wave, we think of, there's geostrophic modes and inertial gravity modes, right? And we think about the geostrophic modes are modified in the Ekman layer, so it's something a little bit different in the top few tens of meters maybe. And I'm saying, well, that also applies to the near inertial, well, the inertial gravity modes are also modified by friction in the upper layer. And so when you're thinking about, wave vortex or wave-wave interactions in the surface layer, it might also be useful to think about you know, the frictional part and the non-frictional part of the waves and the frictional part and the non-frictional part of the vortices, and you have a few more modes to play with when you're doing this kind of decomposition.
Thanks. In the two-layer slab with the slab on top, you do have a first mode baroclinic. You can have first mode baroclinic waves too, right? So did you look at all of the coupling between the mixed layer and those waves?
I don't know. We probably did a little bit, but I don't remember it. Right?
Because some of the energy coming out of the mixed layer could be going into that. Right?
Yeah, I mean, that model, we didn't really look at the energetics that much because it's an F-plane periodic, and so energy goes into the barotropic mode and inverse cascades, and if you don't put a huge damping to kill that, you get just a big eddy in the domain very quickly. You know, in the real ocean, the inverse cascade's going to sort of slow down because of the Rhine scale, and it's going to interact with the western boundary. You know, I like to think of a geostrophic turbulence in the Gulf Stream extension, making big eddies, but then they slam into the boundary and get sheared out into filaments, and so the kind of a recycled and spit back out at smaller scales again. But in a periodic model, you need some artificial mechanism like a bottom drag. We actually use an inverse Laplacian to kill the barotropic mode. So
yeah, I guess I'm also just thinking of the near inertial waves near inertial internal waves in mode 1. That might be, maybe that's how the eddies kill.
Yeah.
The eddies
So we could have
them.
looked at the near inertial internal waves, and we just didn't. Right. I thought
because I guess the eddies are where you get convergences in the mixed layer. And that's where you're coupling to the
so there's no mix. There's a slab layer, right? I guess you can call that but it's just the whole layer is constant density, right? But you're right. We could have looked at high frequency, shallow water way. You know, the first mode, shallow water. We could have split that into high and low frequencies and looked at. We probably did. I just don't remember it. But yeah.
All right, let's thank David again.